Lastly, we are going to talk about the concept of the embedded Markov chain. Now, if you remember, we had defined the probability V sub ij of H, and it was the probability that upon exiting state I, the Markov chain enters state J. That was the probability. Now, if you take the limit of this probability as H goes to 0, we had we had derived this probability as V sub ij equals Q sub ij divided by minus Q sub ii. This was the value we had computed earlier. Now, if you consider V sub ij components, and if you write it as a vector, the vector V, okay, is obviously a stochastic matrix because, well, you will have, let's say um, uh, let's say for row number 1, that will be Q1, 1. Well, I should start from 2. Q1, 2 divided by minus Q1, 1. Q1, 3 divided by minus Q1, 1. Q1, 4 divided by minus Q1, 1, dot, dot, dot. Let's say Q1K, let's say you have K states, divided by minus Q1, 1. So we have Q1, 2, Q1, 3, Q1, 4, etc. up to Q1K, all of them one by one divided by minus Q1, 1. But remember, Q1, 1, or rather minus Q1, 1 is equal to the sum of all these, Q1, 2, Q1, 3, etc. Because the row of that Q matrix is going to be is going to have the sum of 0. Okay, so uh, this matrix V, when you add it up, you see all rows add up to 1, right? Because at position 1, you will have a 0, and all the rest will be Q1, 2 divided by minus Q1, 1, Q1, 3 divided by minus Q1, 1, etc., etc. Okay, so all components will be in this form except VII's, which are going to be 0. Okay, so that describes a stochastic matrix. All the components in a row are probabilities which are greater than 0 and less than 1, and they all add up to 1. So this is a stochastic matrix. By definition, it defines a discrete time Markov chain. So we call this discrete time Markov chain as the embedded Markov chain of the continuous time Markov chain. So this embedded Markov chain, it captures the behavior of the continuous time Markov chain at the state transition epochs. Okay? In other words, it's a snapshot of the continuous time Markov chain with each holding time treated not as a specific amount of time duration, but as one single slot. Okay? So again, let's copy this matrix here. We have from state 1, 1/2, and 2. So we had transition rate of 1/2 to 2, and here to 2. Again, 2, 2, and 1. So this is 2, this is 2, and this is 1. Yes. So let's take this continuous time Markov chain, okay, and compute the V values. Again, if you write V, this will be a 3 by 3 matrix. From state 1, 1 to 1 will be 0, and 1 to 2 will be this divided by that and the sum of these two. So that will be 0.2, and this will be 0.8. Okay, so this is 1/2 divided by 1/2 plus 2, and this is 2 divided by 1/2 plus 2. Okay, similarly, from state 2, when you exit state number 2, you definitely go to state number 1, right? So this will be a 1 here and zeros here. And state number 3, this transition rate to state number 1 and state number 2 are equal and 2. So that means this will be 1/2, this will be 1/2, and at 3 it will be 0. Okay, so this is the V matrix, and as you see, it's a stochastic matrix. All rows add up to 1. Therefore, it describes a discrete time Markov chain. If you plot it, let me put it here, 1, 2, 3. So here, from 1 to 2, probability is 0.2. This probability is 0.8. From 2 to 1, this probability is 1. And from 3, this is 1/2, and this is 1/2. This is the embedded Markov chain of this continuous time Markov chain. Now, what it represents is the state transition probabilities, not with respect to time, but with respect to states at the transition instance. Okay? First of all, it does not have self-transitions because, while a continuous time Markov chain, when it exits a state, it does not go to itself. As the name implies, it's exiting that state. Okay? So this embedded Markov chain captures the behavior of the Markov chain at the very transition instance. Okay? But there is a very close relationship between the continuous time Markov chain and its related embedded Markov chain. Because if the embedded Markov chain is ergodic, well, if you should remember the conditions for being ergodic for a discrete time Markov chain from last week's class, if this embedded Markov chain is ergodic, that means it has a steady state distribution, in which case this continuous time Markov chain is also guaranteed to have a steady state distribution. Okay, so there's a very close relationship between the continuous time Markov chain and its embedded Markov chain, especially in terms of steady state distribution.